Hi everyone, welcome back to the video series. We're going to be taking a look at private IP addresses or IPv4 addressing in this particular module. What is the need for private IP addressing? With the expansion of the internet, the number of addresses that IANA had at its disposal to giving out to public IP addresses was dwindling very fast. Everyone wanted to be on the internet. There was an explosion of smartphones, every device wanting to be connected to the internet. The addresses are depleted. So in this particular module, we'll take a look at how IANA handled that situation. Although it is still a work in progress, but they have, for the time being, settled it and allowed devices to connect up on the internet uniquely. How do they accomplish doing that? By the help of these addressing called private addresses and a concept called NAT. So let's go ahead and take a look at the problem first and the IPv4 address assignments, how they're done and what the problem is. And then we'll take a look at IPv4 addressing and NAT, how it solves the problem, and what are the different private addresses that have been reserved in the three unicast address spaces that we have, the Class A, the Class B, and the Class C address space. What are the private addresses that we have in these address spaces or classes? So first of all, let's go back and take a look at the problem so we can solve it. The problem that happened was when IP addresses were starting to get assigned to different devices, IANA had no idea the popularity of the internet or where the internet would grow to. It basically blew away all the expectations of anyone that wanted to connect up to the internet in terms of what it wanted to do or what it was meant to do. So because of that, IANA had to do certain things to allow the internet to still grow, but at the same time not get IP addresses depleted. So what they ended up doing was they create a special address space that would be used by people on their internal network when they're not connecting to the internet. But when they connect up to the internet, rather than assigning each and every individual device a specific IP address, they introduced this new concept that allowed IP address translation to be done from this private address pool that would only work on the local network versus the internet. And that communication mechanism, that mechanism that allowed that to happen, was called the network address translation, or NAT. So the purpose of NAT was to translate this private address space that would be used on the internal networks, and when they wanted to go out to the internet, they would be translated to a smaller range of addresses or a smaller pool of addresses, so that would conserve the address space on the internet. I'll give you an example of that. Let's say I have a home network. On the home network, I have my access point over here. The access point would be assigned an IP address by the ISP. If the ISP assigned me a specific address and that would be attached to my AP, would not be used by somebody else, that would be a problem because every device that now had to connect to the internet would have a dedicated IP for them. What they did, rather than doing that, is they said, okay, let me go ahead and assign this end user an IP address, but I'm going to do it dynamically in the sense that I'm going to assign this address to him. Let's say the IP address that was assigned was 201.1.5.1. I'll assign him a single address, first of all. And not only that, if he's not using it, I'm going to take it away if there's an idle time that he's not been doing anything with that IP for a certain amount of time, and different ISPs have different timers for that, maybe for 5 minutes or 10 minutes. Some people wait till 30 minutes. What they do is, if they see no activity on that link, they pull that IP address away from him and give it to someone else, another user, another individual user that wanted to use the internet. Because he's not using it, I'll give that IP address to him for that time being. So for that point, at that point in time, he is the one that will own that address. Now let's say this guy comes up and says, hey, I want to communicate to the internet. The ISP will dynamically assign him a different address. Let's say 201.1.5.2. So now the same address was rotated between two different devices. Whereas 5.2 in the previous scheme of things was assigned to a third AP or a third individual user. Now he's not using it, I can play around with it. So I can juggle these pool of addresses between different individual users, only giving addresses to the ones that are using the internet. If they're not using it, I'll pull the address back and put it back into the pool to assign to somebody else. That was the first thing. But the thing is, on this home network, a personal network behind the AP, it's not one user that's logging in. There's multiple users that might be logging in. So that's where NAT came in, where the IANA told the individual users or the manufacturers of the AP or companies, hey, listen, what I'm going to do is I'm going to give you a single IP address. What you use on the inside is one of those private IP address spaces. I will show you what those private IP address spaces are that are used within the internal network. These private IP addresses were defined in a special document, a standard known as the RFC 1918. This is a special document that was written specifically depicting all the different addresses that could be used within the internal network. They used a certain type of address in the Class A, Class B, and a Class C network, which defined what addresses were private. And it indicated to the service provider that, hey, listen, these private IP addresses cannot be used on the internet. They're only to be used within the private company. So that allowed the second company to use the same pool of addresses. So for example, I have a Class C address over here, 192.168.1.0. The entire network, which could host up to 254 hosts, was assigned to this internal network. But as soon as it wanted to go to the internet, because this address was banned from being used on the internet, the AP had to translate that address to his public address. Let's say his public address at that point was 201.1.5.2. When the packet came in, it would have a source address of 192.168, let's say 1.5, going to some server on the internet. What the AP would do is it would perform a translation of that address, where this address would be translated and sent out using the access point's public address, whatever public address was assigned to him on this interface. So although you had a single address, multiple devices on the inside could use the same address to go out. And this process was called NAT, or there's another flavor of NAT called PAT. We'll discuss that in detail in a later section. But overall, this concept is known as the network address translation capability, or the NAT capability. So this allowed you to have private addresses internally, whereas when they went to the internet, they would use the public address. Same address, 192.168.1.0, could also be used behind this AP. And although I might have 5 or 10 different devices behind the AP, when they went out, they would use a unique address. So all these different devices would use the same address. So you guys saw over here 2 ways of conserving addresses over here. Number 1, if the user is not using the address, pull it out and give it to someone else. So I don't need to have statically assigned an IP address and block that IP address for a particular user. If he's not using it, I'm going to use it somewhere else. The other thing, rather than giving this home user 4 IPs or 10 IPs or 20 IPs, I just give him 1 and use the translation capability called NAT, network address translation, to translate the private address to the public address. For this to work properly, you needed to make sure these addresses were not used on the internet, so they stopped using these addresses, the private addresses, which were defined in RFC 1918 on the internet. So this is a special document for standards that was written specifically to define what addresses could be used as private addresses. So that's what the whole gist of this chapter is, or this video is over here. But at the same time, I'm going to show you what are the specific private IPs in Class A, Class B, and a Class C network. So to recap what I just talked about, I have 2 slides for that. Number 1 is how the IP addressing took place. As I said prior to starting on my demonstration, that the internet addresses were getting depleted. To counter that, IANA reserved a certain set of addresses. I'll show you which ones those are for internal use within the private networks. And those internal addresses were defined in a standards document. The standards documents for internet standards is set with this acronym, which stands for request for comments, which is basically a standards document. And the standards document that specifically pertains to private IP addresses was document number 1918, collectively is known as RFC 1918, to define the private addresses that can be used on the internal network. Those addresses will not be used on the public internet. All right, but in order for this private address to go to the outside, they needed to have some type of translation done, because the private addresses would not be able to be, you would not be able to use the private addresses on the internet, and that capability was called NAT, network address translation. All right, and that's what the next slide depicts over here, or talks about over here. The ISP assigns dynamic IP addresses to a client from a pool of addresses. When the client is not using the address is returned back to the pool, as I explained to you a while back, or 2 minutes back. This allows you to use public addresses more efficiently. This allows you the ability to have less number of addresses assigned to a bunch of different hosts. I can assign one address and then use the same address for multiple devices. All right, and not only that, I'm not statically assigning or binding an address to a particular individual user. I can reuse this address with some other people when that individual user is not using it. All right, and the translation, as I talked about, that would translate the internal address to the external address, is called NAT. So multiple internal devices could share the same public address on the internet. This would also allow you to conserve or save on IP addresses on the outside. As I said, we'll do a detailed video specifically on how NAT actually works. How do you configure NAT? But the objective of this video is not to go into NAT, but to understand the IP addresses that are private IP addresses within your private network. And what are those? So as I said, the RFC 1918 document basically listed the different IP addresses that could be used as private addresses in each one of the classes, Class A, Class B, as well as Class C. Let's go ahead and take a look at what are those addresses in A, B, and C that are going to be used as private addresses. So first one, Class A. There's only a single address, single network in Class A that is a private address. That address, that network in Class A is this network 10.0.0.8. So this address 10.0.0.8 cannot be used on the internet. It has to be used within the company. So if you have a large network inside and they all want to go out to the internet, internally I can give them the address 10.0.0.0. So this address is not going to be used on the internet. It is only going to be used within the network, within the company network. When this type of device goes to the internet, it will be translated using either NAT, and as I explained to you, there's another flavor of NAT that we'll also discuss later on, which is called port address translation, or PAT. And I will go into detail in a video about NAT and PAT. At this point, my objective is to make you understand that in the Class A addressing space, the only network that is designated or set aside for private addresses is the 10 network. The 10.0.0.0, as you guys have learned from the previous video, that on a 10 network, which is a Class A network, the default subnet mask is 255.0.0.0, or you can also write it as /8. So that is the network that is assigned or dedicated for a Class A private address. If you don't want that number of hosts, you can go to Class B private address space. What does a Class B private address space look like? Well, over here, because I have more networks to give, they have reserved about 16 different networks that could be private networks in the Class B range. What are those different networks? It starts with 172.16. As you guys already know now, that 172.16, by looking at the first octet, is a Class B network. That means the first 16 bits over here are the network bits. So this is my first network that is a Class B private network. The second one is 17. Third one is 18, so on and so forth. all the way to 172.31. So a total number of 16 addresses, 16 to 31, are private addresses in the Class B range. So if you want to have a bigger network, you're going to have, a smaller network than a Class A network. You don't want to have 16 million hosts on that network. You might as well use one of those private addresses, the Class B address range. So that is between 172.16 through 172.71. 31. Those are the 16 addresses that are used as the private Class B addresses. All right. Similarly, because there are more networks in Class C, there are more Class C private addresses. What are those Class C private addresses? As you guys know already now that Class C, the first 24 bits are your network bits. So the first Class C private address is 192.168.0.0/24, which is basically 255.255.255.0. The second one would be 192.168.1.0, 2.0, 3.0, all the way to 192.168.255.0. How many of those networks do I get if I start from 0 to 255? The total number of networks that are Class C private networks are 256 networks, all the way from 192.168.0.0 to 192.168.255.0. This is wrong. I need to fix this over here. Let's do it real quick. .168.255 is the range of Class C private addresses. Again, in order for these addresses to go on the internet, they will get translated by the device, the router that's connecting to your ISP router. A typical example of this, I'm going to show you a home network as well as an office network. A home network, generally what happens is the ISP over here is going to assign your AP or a router a public address, a single public address from a pool of addresses. So if another end user tries to connect in over here, he will also get an address assigned, let's say 201.1.5.2. If this guy is not using it, he will take that address and assign it to another end user. So this guy could technically get the same address assigned to it if he is not using it for the idle time. Now, once the address is assigned over here, he gets an address of 201.1.5.1 assigned to it. His internal address space that I've given over here is from the Class C range, 192.168.1.0. So this PC might be 5, 6, 20, 21. On the outside, it's using 201.1.5.1 as a public address. So if he wants to communicate to, let's say, google.com 199, which is a public address, .1.2.3, I just made it up. He would start the packet out by using his address as a source. So his source address will be 192.168.1.20, 192.168, and the first two octets of a Class C address make it a private Class C address. When it tries to go to the router has a public address assigned to it. He will take this address and translate that address to the corresponding public address that has been assigned to him, which is 201.1.5.1. So when he gets a request, he does not get the request from 192.168.1.20. Instead, he gets a request from, rather than getting it from 192.168.1.20, he will get the request from 201.1.5.1. That is on a home computer. On a on a company network, let's say the company wants to go out to the internet, connect up to the internet, he has 1,000 hosts. Okay, 1,000 hosts on the inside, but when he tries to go out through the internet, he has some servers that he wants to statically assign addresses. So you cannot do a dynamic translation. So over here, you do assign a pool of addresses to this company. It is static. You're assigning about 254 public IP addresses to the host, but at the same time, what you're doing over here is that you're saving yourself, rather than assigning 1,000 hosts, you're only assigning 254 hosts to that particular public IP. Okay, so you're still saving a whole bunch of different addresses. Although it's not dynamic, it's still static. So this company will have a range of 195.111 through 254 as its public addresses. What he can do is he can statically say the DNS server is 195.115, this guy is 116, and so on and so forth. And the rest of the PCs, he can say you have up to 1,000 PCs, they can use addresses from my pool. So I've reserved 2 addresses for my DNS and web server. Let's use them as the last 2 addresses in that pool. So the DNS server, let's say, is 253, and the web server, I'll put it as 195.1.1.254, and I'll set a pool of dynamic addresses from 195.111 to 195.1.1.252. So these 252 addresses can be used by these 1,000 hosts to go out to the internet. So when the packet leaves, for example, I'm leaving the packet as 172.16.1.11 as a source address going to that Google server over here. The router over here will intercept that request and translates that 172.16.1.11 to the public address from that pool. Again, the main objective over here is to save or conserve on the addresses used on the internet. 2 different ways of doing it. One is assigning a single public IP, which is dynamic, can be changed and given to other people if the end user is not using it. Internally, I have a bunch of different users using the same dynamic IP. Here, although I'm doing it statically, I'm assigning a static pool to the company. But although it's a static pool, it's still conserving addresses because this company requires a whole bunch of different addresses to go out. I'm only giving it 254 hosts versus 1,000 hosts. Could you have just done the dynamic thing with the company as well? Yes, you could, but because I have a server over here in the company that might need to be accessed from the internet, you cannot give dynamic addresses to these servers, because that way the people that are trying to access the servers would not know what the IP address of those servers is. So that's why you want to give it a static IP, translate it, but give it a static IP. At the same time, it also handles all the 1,000 hosts that are going out with just a pool of 252 public addresses. So you're still saving about 4 times the number of addresses over there. We'll go into more detail about NAT as we go through the course, but it's my main objective in this particular video is, again, as I say in all my videos, what is a takeaway? What do I need to learn on here? Is that to conserve addresses, what the INI has done is it has assigned certain addresses that can only be used on the inside of the network, so that I can conserve those addresses going to the outside. How does it conserve it? By not assigning a static IP to individual users, or for companies not assigning all the IP addresses that it requires, giving them a smaller pool and having them translate those addresses when they go on the internet. These addresses are defined in this comment, a documentation or standards document called the RFC, request for comments, and that specific document for your NAT is 1918, which defines the addresses that are private in the A, B, and the C classes. That's what I wanted to get out of this video. That's what I want you to have as a takeaway from this video. All these things will all come together as we go through the course. Let's take a look at the review questions at the end of the module. What is the name of the standards document related to the private IP addressing? That is called the RFC 1918 addressing document. That's the standards document for the private addresses. What is the name of the process that translates private addresses to public addresses on the internet? The process is called NAT. What is a class A private address? It's a single address, 10.0.0.0/8. That means it has the first 8 bits as the network bits. In the class B, there's a range of class B private addresses. Starts with 172.16.0.0/16 all the way to 172.31.0.0. So a total of 16 networks that are private networks in class B. In class C, the range of addresses starts with 192.168.0.0 as my first Class C private address, and the last one in that range is 192.168.255.0/24, which is a total of 256 networks. So in Class A, a single network, Class B, 16, Class C, 256 networks. All right, that is the end of this video. Hope you guys enjoyed it. See you in the next video.